Hello, ladies and gentlemen. Welcome to ICANX Talks, Connect World and the Universe. No matter where you are, we come back and this Friday's talk. So today is a big day because today is a special issue for Huazhong University of Science and Technology, the 70th anniversary. So this will be a special issue, and it's especially for me because I'm the graduate student, from Huazhong University of Science and Technology many years ago. And this is my alma mater. I'm so excited, to introduce these special issues and very warm greetings to, our university, our friends all over the world and to this talks. So this is Alice from Beijing. And this was also the beginning of October. So in October, we're going to have several, talks on this, October session. This was the first week of October. We're going to have this, I can have a special for celebration of past the anniversary. And next Friday and the week after, we're going to have the writing start. So we will have 2 weeks. 1 week is for the PhD candidate. Another week is for the postdoc and the faculty and PI. So this will be 2 weeks for this writing start selection and defense. You will see many new faces. And the last week of October, we're going to have a big name from Germany. He's one of the big names in the 3D printing technology, Martin Wagner. So this was all of this October's talk we name as this season was shining light. See all these shining, names on this stage, on these shining technologies on this stage. So we go to host, many young students and young friends here. And today was the first week of ICANX, in October. So the first week is a big, event. We have this, celebration for Huazhong University of Science and Technology, the 70 years, anniversary, 70 years. So we choose 7 peoples. Yeah, we got these global, pictures on this is we have the students from different parts, they graduated from Huazhong University, but they got to, go to the world. So we, these 7 people was from different places. Me now is in Beijing, the Peking University. I'm a graduate from Huazhong University many years ago. And my colleague, Chen Rong, he's, in another way, he's a faculty in Huazhong University. So it's a support Huazhong University, and now he's a big name, super professors there. And we have a Gong Chen was from USA. We have Quanquan was graduated from Canada, and now is young PI in Peking University. We have a Zhu Ying was from Australia. We have a Zhu Xueming. Dr. Zhu is graduated from German, got his PhD, and now he's leading entrepreneurship. Yeah, it was doing a lot of nice work. And we have Ouyang Zhufeng was from Japan. I also graduated from Huazhong University and got PhD at Japan. So you see these pictures with the 7 people pick up, for this 70 years anniversary. And now I'm going to introduce, my best friend Chen Rong, and now he's, big professor in Huazhong University of Science and Technology. She is going to talk about something, happening in Huazhong these days. Please, Chen Rong.
Thank you, Alice. You know that yesterday we have the successful conference to celebrate the 70th anniversary of Huazhong University of Science and Technology, HUST. Like the PPT says, we received congratulations and the blessings from all over the world. And more importantly, I think the faculty, staff, students, and most importantly, alumni all over the world have shared the happiness. HUST, situated in Wuhan, the capital city located in the heartland of China, is also a historical city with 3,500 years of history. It's also an industrial, education, and cultural centers of China, and the hub of air, water, highway, railway, and high-speed train transportation in central China. And the spirit of Wuhan is brave in innovation, commitment to excellence. So does that for HAST in various historical periods since its establishment in 1952. Over the past 17 years, trees towering on Yujia Mountains and HAST become the flourish and cultivate 700,000 alumni all over the world. And today, we really thank the IKX platform to help connect the world and the universe. And we have the great fortune to connect the alumni all over the world to celebrate Haas's birthday. So we have two Haas alumni, both are outstanding young professors, bring their most recent research for today's academic feast. The first speaker today is Professor Quanquan Pang from Peking University. Professor Pang received his bachelor degree in material science and engineering at Haas in 2012. Master and PhD from University of Waterloo in chemistry in 2014 and 2017, respectively. He was a postdoc associate in material science and engineering at MIT before he joined the faculty team in Peking University. Professor Pang's main research interest is studying new battery systems, solid-state batteries, and sulfur batteries for electrochemical energy storage and electrical vehicle. He's Clarivate highly cited researcher with publications in Nature, Nature Energy, Joule, PNAS, etc. And today he will bring the presentation, Sulfur Electrochemistry and its use in rechargeable battery. So Professor Pang, the stage is for you.
All right, thank you, Professor Chen, for your introduction. Can you guys hear me clear?
Yes.
Okay, cool. And I'll also thank Alice for the invitation. So it's really a great honor to give this talk on the ICANX platform. I think it's also an even bigger honor to speak as we celebrate the 70th anniversary of Huazhong University of Science and Technology. Yeah, I am the 2012 graduate from the School of Material Science and Engineering at HAST. And it feels very honored to come back and speak about my research. So let me get into my research directly. So my talk today is going to be focused on the sulfur electrochemistry and also its use in rechargeable batteries. So speaking of batteries, we have to talk about energy storage, meaning that we have to store the energy in some format. And the final goal of energy storage is to be able to utilize the renewable energies as efficient as we can. You know, we have very good technologies to generate energy from the wind and the solar, but there's a problem with the wind or the solar. Because you know the wind doesn't always blow and the sun doesn't shine in the night. That's why we have to store the energy so that we can store them and use it for when the energy is not available. And that's where the energy storage come into place. And basically, there are two ways that we can think on the energy storage. One is the one that that is on the right, is that you can convert the electricity directly into some chemicals, for example, the alcohols, the methanol, etc., that we can carry. We can use as we use the petroleum. The other way is to use batteries, meaning that we store the energy in two electrodes that has a different redox potential, so that we can store the electricity in the format of chemical energy, and that's what we talk about the lithium the batteries. And you know the most widely used batteries for now is the lithium-ion batteries. So let's talk about the basic principles of the lithium-ion batteries for a little bit. A lithium-ion battery, meaning that we use lithium ions as the charge carriers, and a typical battery has a positive electrode, which we also call cathode. a negative electrode, which is also called an anode, and there's also the electrolyte. For the cathode part, we have lithium iron phosphate. For people who know a little bit about lithium ion batteries, you probably know lithium iron phosphate that we use. We now have used very widely in electrical cars, like in BYD and other cars. We also know lithium cobalt oxide, which everybody has that in their cell phones and computers. And on the other side, we have graphite and lithium metal. So this is what the 2019 Nobel Chemistry Prize, or 2020, sorry, that the Nobel Prize in Chemistry is awarded to those three very important contributors to the lithium-ion batteries. So, but what if we go beyond lithium-ion batteries, meaning that if we wanted to use the batteries very widely, we can think of two applications. One is the electrical vehicles, and the other one is the grid energy storage. So the electric vehicles, we're talking about energy density, meaning that we want to have higher energy, like higher watt hour per kilogram of our battery. And we want to use the battery to have high power, and also we want the battery to be cheap, like low cost. And on the other side, we have very important applications. For example, the grid scale, meaning that we want to use the battery for the grid, for the solar, for the cell, for the wind. And if we want to go beyond lithium, meaning we want higher energy density, where we want a lower cost, there's some targets that we can do. For example, you can continue on the lithium mine, and you can go to high nickel or lithium-rich cathodes. But there's also other options. For example, showing you here that you can do sulfur batteries, and I will talk about sulfur for this talk. And also you can go to all solid-state batteries. You can also do aluminum batteries. Aluminum battery meaning that you don't use lithium, but you use aluminum. And that's because aluminum is very abundant, it's very low cost. So I will talk very briefly on the basics of sulfur, and like basically why do we use sulfur? The most important reason is that sulfur is cheap, and you probably know that sulfur is actually the byproduct in oil refining industry, and that's why. And people, like in the old days, people even don't know how to discard the sulfur because there's basically too much sulfur, and people don't know how to use it. And that's why we want to do sulfur battery. And for the chemistry part, we know that sulfur bears many charges, meaning that sulfur can be in -2 valence state. It can also be +6, meaning. And that gives sulfur the biggest advantage is that it can promise very high capacity, meaning that one sulfur atom, you can store many charges. And that's very useful for being used as active materials for batteries. So that comes to my today. I wanted to talk, spend a bit of time on lithium sulfur batteries, the positive electrodes or the cathodes, the electrolyte, and I will talk very briefly on the molten salt aluminum sulfur batteries that we have worked on very recently. So lithium sulfur battery, for its name, it means it uses lithium metal as the anode, and it uses the sulfur as the cathode. And the sulfur has very high theoretical capacity, like 1600 milliamp hour per gram, meaning for 1 gram of sulfur, you can get 16272 milliamp hour. And if you don't have any too much idea about 1 milliamp hour means that you can look at your charger, the portable charger. It probably labels like 2000 milliamp hour, and that means like if we have 1 gram of sulfur, you can probably get 1600 milliamp hour. That's very much. The problem with lithium sulfur is also a lot. And the basic problem is that for lithium sulfur, it has a very complex chemistry. Sulfur by nature has a lot of valence states. The problem also comes with nature is that it has a lot of intermediate species that I will talk about in here. Is that so the lithium sulfur promises very high capacity, but it's also the sulfur speciation is very complex. For example, we have a lot of species lithium polysulfides. This is what we call that is in the cell. And also, this intermediate species, they are dissolved in electrolyte. Dissolved means, so for the lithium-ion batteries, for example, lithium iron phosphate, we know that it's a solid, it isn't dissolved, it stays where it is. But if it's dissolved, it's gonna diffuse in the electrolyte and do a lot of funny things that hurts the battery. And also, as a chemist, we have a very big interest in knowing how the sulfur reacts in a cell. So we're not only interested in making the battery perform very well, we also want to know how the chemistry evolves in a cell. As you see on the right, there are multiple equations that describe how the sulfur converts from, for example, S6 2- to a radical, and all the stuff. It makes the sulfur complex, and this is what we are interested in. So in like almost 6 years ago, we have written a review articles on how to improve sulfur battery even better. And we realized that there are multiple aspects on this. Like, for example, you have to work on the positive electrode, make the electrode very conductive by using carbon, and you have to optimize the electrolyte. And also, the very important aspect is that we have to work on the lithium metal, and we'll talk about this a little bit also today. From all these aspects, we try to solve the problem, and the biggest problem that we began several years ago is to deal with the shuttling or the dissolving of the polysulfides that I've talked about, the intermediates, like how to stop them from dissolving, how to stop them from diffusing into the electrolyte, and how to stop them reacting with other parts of the battery. So the start of lithium battery like 2 decades ago is to use porous carbons. As a material scientist, we probably know a lot about porous carbons, that we hope to confine the polysulfides in the pores of the carbon so that they don't diffuse so freely. But it turns out the porous carbon relies only on the physical confinements, like basically use the pore, the space, and that's not enough. So we have designed a strategy to chemically absorb these polysulfides. And the specific materials that we have invented a reduced titanium oxide, which is titanium 407. And this is a electronically conducting metal oxide, and that we later use, for example, XPS to confirm that there's very strong chemical interaction between the polysulfides and the titanium oxide. And that can help us confine the polysulfides very nicely and give us very good cycling capacity, meaning that if we use this material, the polysulfide will very largely stay where it was, and it doesn't diffuse. And that's why the sulfur can stay and function over a long period of time. And later, we also try to do something more practical, meaning that we want to use some light host materials. Like we want to, titanium is more or less heavy. And that's why we wanted to go to something like a magnesium boride, which is a light material that is also electronically conducting, and that is also able to chemical absorb the polysulfides. And we are able to achieve very high % of sulfur in the composite, so that's the total electrode can supply a very large capacity. Okay, so that part is about the cathode. So the basic strategy is to stop the polysulfide from dissolving. But on the other side, we can also think of something else to stop them from dissolving. Meaning that if you want to stop something dissolve in a solvent, you can also you better change the solvent. Like if you invent a solvent that doesn't dissolve the polysulfides at all, that should solve the problem from the beginning. And that's why we have transit our focus into the electrolyte of the battery. And the practical target is also to reduce the volume of electrolyte in a cell. the electrolyte only serves to conduct the lithium ions. It doesn't contribute to the capacity. So that's why I want to use as little electrolyte as possible. So the question was, can we design an electrolyte that does not dissolve the polysulfides and therefore does not require too much electrolyte volume, which at the same time is also not reacting with the lithium metal. And the problem, if we go back a little bit, is because lithium metal is a very reducing metal. Like if you put lithium metal in any solvent, it's going to react to the solvent, and that's going to cause the electrolyte to decompose, and gradually the electrolyte is going to be consumed up, and the battery is going to die. So we wanted to design electrolyte that can function in these two roles. One, does not dissolve polysulfides. Two, does not react with lithium metal. So we come up with a design of the electrolyte, and that's what we currently call the sparingly solvated electrolyte. And the electrolyte is basically one that is dissolves a lot of salt. Here is lithium TFSI. So if we increase the salt contribution, the salt concentration to very high, closely to saturated. If we do a molecular dynamics, we can clearly see the electrolyte has changed its structure. It become, and if we basically what happens is the free solvent has reduced a lot. And if we can reduce the free solvent, we can easily reduce the solubility for polysulfide, and that's what we see. Like if you see the colors, we can know that as we increase the contribution, the polysulfide dissolve very little. And at the same time, the electrolyte become less flammable, and that's very important for the safety as well. And what happens to the battery, to the electrochemistry, is that if we can reduce the polysulfide solubility by a lot, and we can change the sulfur chemistry very, very significantly. And if you look at the discharge voltage profile, which every single battery scientist looks at for the batteries, you can clearly see the change of the voltage as we increase the salt contribution. And to make it more concise, is that the conversion of sulfur to lithium sulfide during discharge has been more kinetically promoted. And also, what happens is that the surface passivation by the lithium sulfide has reduced, that the battery does not go through very significant increase in impedance over a long-term cycling. So basically, with the reduced solubility, we have achieved the quasi-solid state conversion instead of a liquid-solid reaction, and that's the basic chemistry of the cell. And also on the lithium metal side, we have basically changed the plating behavior of lithium metal by a lot, and that's why we see a lot of big particles instead of this dendrite. And for those people who know a little bit about lithium batteries, we know that dendrite is a big problem for the safety. And if we cannot solve the dendrite, we will never be able to put our lithium metal in our car. So with this kind of electrolyte, we can make the lithium sulfur battery work more and better for longer cycling if we use a very little amount of electrolyte. So here ES ratio equals 5 million, that's very low electrolyte volume. But this is what we have achieved a few years ago, and now we're working on to make the battery even better and sustain hundreds of cycles. Okay, so that is about the lithium sulfur batteries, meaning that we're still using lithium. But we're using sulfur because that can give us a higher energy density, and sulfur itself is being cheap. But what if we move one step further towards lower cost? Is that we can use aluminum as the anode and not lithium. And we all know that in the past 1 year or so, the lithium price has increased by many times over the past few months. and that makes like very little profit margin for the lithium battery industry. And that's why people are looking, are very much looking forward to see a battery that does not use lithium. So here, if we go to switch from lithium to aluminum, if you look at this figure, that means we can still get a very high capacity. We can still get a very big, high milliamp hour per gram by using aluminum. But we know that aluminum is very abundant, it's very low cost. So that's why we are very keen on making aluminum sulfur battery work. And also, if the battery is cheap, it's gonna be very attractive for the grid scale energy storage, because for grid energy storage, there's gonna be tons of batteries used, and that's why people have to be paying a lot of attention to the cost. But speaking of aluminum sulfur batteries, it's not invented only recently. It actually can date back to the 1990s, where people have worked on aqueous aluminum sulfur batteries. But that battery, and that aluminum aqueous battery is actually only a primary battery, meaning that you can only discharge the battery, but you cannot recharge it. And the past few years have seen aluminum sulfur batteries, but mostly of them are in the using the ionic liquid. Ionic liquid means a liquid that is consisting of ions, but it can melt at room temperature. But the room temperature batteries are very sluggish at room temperature. That's why we have invented a battery system based on the inorganic chloroaluminate melt electrolyte, which basically a molten salt that can melt at about 100 degrees C. So to make the story short, we are very surprised to see that the molten salt can support very stable aluminum plating and stripping, meaning that it can function for the aluminum batteries, and it also can enable the sulfur chemistry. What is even surprising is that we see very unexpectedly see 1 order of magnitude higher exchange current for the aluminum symmetrical cell, meaning that if we switch to molten salt, it can enable at least 1 order of magnitude higher power density if we use molten salt. And if you look at the basic science of the or basic chemistry of this molten salt, you can clearly see that from the video. See that in the molten salt, which is shown in here on the bottom, is that it contains a lot of this long chain or higher order clusters, the aluminum 4, aluminum 3, 13, for example. And this key species here is what we found is the key species in the electrolyte that enable this 10 times higher power density. And that's because we think this high order aluminum chlorine clusters can enable very fast dissolution, meaning that for the aluminum ion to come out of the electrolyte and participate in the reaction in the electrode, it has to go through a dissolution step. The dissolution, the energy that we have calculated is that this long chain, for example, aluminum 4 and aluminum 3, they're very easily converts to aluminum 2 chlorine 6. And this cluster is very key species during the dissolution of the electrolyte. For example, if you look at the video on the left, you can see that these aluminum 4 clusters, from time to time, it break the bond and form this aluminum 2 chlorine 6. And this species here is very important for dissolution. I won't be able to talk much about the details on that chemistry, but if you're interested, you can look at our articles, and that's very nice to show that the dissolution chemistry. But if we continue on the battery side, this electrolyte can enable very fast aluminum plating and stripping on the anode side, and also we don't see the dendrites that as I talk about is very dangerous for the battery, meaning that it can very safely work in the molten salt. And if we do the synchrotron actually absorption study, to study what I just talked about that is very interesting is the speciation of the sulfur in the cell. We can clearly using X-ray absorption and X-ray diffraction, we can clearly see that we form this aluminum polyselenide in the electrolyte. That is very important for the reaction kinetics. So on the performance side, our aluminum sulfur batteries can perform very well. For example, at 110 degrees C, it has very large capacity, 1400 milliamp hour per gram, a very flat voltage plateau, and a very low overpotential in here. And also, the battery can go through very fast charge, meaning that you can, for example, we can even go to 200 C, where 1 C, like if you can charge a battery at 1 C, meaning that you can finish charging in 1 hour, and that's what people care about, like how long does it take to fully charge a battery? So meaning that we can even charge the battery within 1 second using this chemistry. And also, this battery can sustain hundreds of cycles at a very high charging rate, for example, 5 to 10 C, and this battery can still function very stably. And on the discharge side, for battery to be able to use any storage, it has to also be able to discharge very fast. And our battery can also discharge very fast. As you can see here, that you can discharge the battery at easily at 20 C rate. Okay, so coming to the end is the estimated energy density and the material cost. As I talk about this battery, the most important advantage of batteries is very low cost. And here you can clearly see our estimated material cost is only 12 to 16% of the current lithium-ion batteries. And to make the battery, we're estimating that we can the cost is only about 35 to 40% of the current lithium-ion batteries, and the energy density is about 10 to 20% higher than the lithium-ion phosphate battery. And last but not least is the safety of the battery, because we use inorganic electrolyte, meaning that we don't use any organic flame or solvent, and the battery is thus very intrinsically safe. So I want to end my talk with a little bit of outlook for the sulfur electrochemistry with 2 points. First is that the abundance and also the low cost of sulfur is the primary drive that is going to make it widely available in electrical vehicles and grid energy storage. And that's because I, as a scientist, I actually believe that the cost is the main driver for a battery to be really commercialized in a market. And on the other hand, in the meanwhile, the sulfur chemistry is very complex. As I've talked, I'm probably not have not convinced you that it's so complex, but it's very complex as a chemist, so that there remains many scientific questions to be answered, and that's why we have to continue working on the scientific side of the battery. So with that, I want to end my talk by thanking my lab members and by thank the foundations for the research, and last, I want to again celebrate the 70th anniversary of Huazhong University of Science and Technology, and let's enjoy the moment. Thank you.
Thank you very much, Professor Pong, for this great talk on sulfur rechargeable batteries. You talked about the cathodes, high performance electrolyte design for the lithium sulfur batteries, as well as the low cost and highly safe aluminum sulfur batteries. So this talk gave us great promises under the current energy crisis, and we will save all the Q&As after the second talk. Thank you very much.
Thank you, Professor. Stop sharing.
Okay, so now let's turn into our second speaker. So yesterday, during the celebration of 70th anniversary conference, Professor Gong Chen from MIT mentioned that a young alumnus visited him. So that is Wei Gao today. So Professor Gao is an assistant professor of medical engineering at Caltech, Ronald and Joanne Whelan's scholar. He received his bachelor degrees in mechanical science and engineering at HUST in 2007, Master in Precision Instrument at Tsinghua University, and PhD in Chemical Engineering at UC San Diego. In 2014 to 2017, he was a postdoc fellow at UC Berkeley. Professor Gao is a recipient of numerous prestigious international awards, including NSF Career Award, Sloan Research Fellowship, World Economic Forum Young Scientist, MIT Technology Review 35 under 35. It's a long list, but due to the time limit, I won't go through the entire long list. So Professor Gao's research interests include wearable devices, biosensors, flexible electronics, micro-nano robotics, and nanomedicines. Today, he will bring the talk, Skin Interface to Autonomous Wearable Biosensors. So Professor Gao, please.
Thanks very much for the kind of introduction, Professor Chen. It's wonderful to have such great opportunity to share our recent research on wearable biosensors. So I graduated from Huazhong 2007, as mentioned, from School of Mechanical Science and Engineering. So currently my lab mainly focused on developing wearable biosensors. As we know, wearables can play a very important role in personalized healthcare because they can continuously collect data from our body and tell us what's going on and what's going wrong with our health. Especially during the pandemic, COVID-19 pandemic, remote at-home health monitoring became such a big deal. But if you look at what are the commercially available health monitors can do, we have Apple Watch, Fitbit, different type of smart band. They can mainly collect the physical activities of vital sign information, but cannot provide more useful information about our health at a molecular level. So we think a major gap, which is also a great opportunity in the field of wearable biosensors, is how can we perform physiological monitoring at molecular level, continuously and ideally non-invasively without accessing blood. In this regard, we are actually looking at one important body fluid, human sweat. In sweat, we are sweating all the time, essentially. It's an important body fluid, continuously we can access non-invasively and conveniently as well. Sweat contains many important analytes or biomarkers, including different types of ions, metabolites, over 30 amino acids, or over 300 proteins, and a number of other vitamins, peptides, hormones. We can also identify different types of substances, including heavy metals and drugs. Imagine that if we could develop a wearable device, we can wear this like this wristband or watch. We can continuously analyze these chemical biomarkers from the skin. We could use this large set of information to perform fitness tracking, disease diagnosis, and very importantly, this larger set of chemical information or molecular information is not previously accessible. If we couple the larger set of chemical information with the larger set of physical information, run machine learning, big data analysis, we will be able to enable numerous fundamental and clinical investigations. So back to nearly 7 years ago already, we reported our first wearable sensing platform. In this case, a fully integrated system that can perform real-time multiplex sensing of multiple metabolites, including glucose, lactate, multiple electrolytes, including sodium, potassium, along with the skin temperature. So this is an integrated system. It consists of reusable flexible printed circuit board and of disposable flexible sensor patch. So they can perform on-site signal conditioning, processing, and wireless transmission. So eventually all the data collected by the sensor can be sent to the cell phone through Bluetooth and displayed on the custom developed cell phone app. We actually have iOS app and also Android app. You can also upload data to the cloud or send the data to the computer through email. So we have performed a lot of human trials to continuously collect this type of data. Over the past 5-6 years, actually, many research groups have made tremendous progress in this field. Today, I just want to highlight several remaining major challenges for wearable sweat biosensors. Firstly, because we want to build a technology facing consumer use, we want to make sure this biosensors, the wearable sensor, can be mass produced at low cost. And importantly, they still should have high performance because many biomarkers in our body fluid present at very low concentration. We need a very good sensor to perform such a continuous detection, and importantly, low cost as well. The second challenge is really, we have so many biomarkers to detect, but we don't have enough good sensing strategy that can perform continuous monitoring. So we can develop many sensors to monitor many biomarkers, but majority of clinically relevant biomarker cannot be detected continuously using existing sensing strategies. Third challenge is, since we're analyzing sweat, you might think of, what if we have skin contamination? What if sweat evaporates? How we can sample sweat to get real-time information. So the last major challenge and also an important aspect of wearable sensor is really we need to find killer applications to validate this sensor in larger scale population, both healthy people and patients, toward health management. So I want to show you our recent progress to address these challenges. Firstly, to get high performance chemical sensor at larger scale at low cost, we proposed a laser engraving approach. In this case, by using CO2 laser engraving, we can make microfluidic multimodal sensor patch at a very large scale and low cost. The mechanism is like this: CO2 laser engraving. If you directly engrave polyimide, the plastic polyimide surface, it's due to the photothermal process. The laser will burn the surface of this plastic from carbon. Basically, it will form this beautiful graphene structure. In this case, we don't need any other material, just use a laser and a plastic substrate. We can patent graphene structures. By controlling the laser parameter, we can control the morphology and the property of this graphene. For example, using certain parameter, we can get a graphene structure that have very good performance toward chemical sensing. We can analyze the very low concentration biomarkers in human sweat. We can also, through certain parameter modification, to prepare some graphene structure that have very good mechanical stability toward physical sensing. So we can also use the laser to cut medical adhesive or medical tabs to form the microfluidics. Because microfluidic is also very important. Think about, we have potentially influence from sweat contamination, skin evaporation. In this case, we put the sensor in the microfluidics, so there is a limited influence from evaporation. We can sample sweat in real time to get real-time information. So in summary, we can use simply laser engraving, this simple approach, to prepare physical sensor, chemical sensor, and microfluidics. The entire actual lab on the skin can be produced at larger scale and low cost. Our graduate student Isabella actually, because of this work, received the Forbes 30 under 30 last year. So this laser engraved chemical sensor had pretty good performance in case of analyzing trace level biomarkers in human sweat. For example, we can use this to analyzing uric acid and tyrosine, two important biomarkers in human sweat. By detecting the oxidation of uric acid and tyrosine, if we apply the voltage from low to high using differential pulses, we can oxidize this molecule selectively at a given voltage. By reading the current height of this oxidation peak, we can get a concentration. Current height has a linear concentration with the target concentration. This laser engraved graphene electrode is much better performance compared to other commercially available electrodes, such as glassy carbon electrode, gold electrode, or screen printed electrode. So this sensor have a good selectivity over many other metabolized nutrients in human sweat. We can accurately and continuously analyze, in this case, uric acid and tyrosine, for example. This laser engraved physical sensor, as I said, can be used to monitor body vital signs. It's also a graphene-based sensor. We can develop a temperature sensor that can measure the temperature changes when you have higher temperature. In this case, the resistive graphene sensor will decrease in resistance. So we can also build a strength sensor to monitor the heart rate or respiration rate. So this type of 3D graphene structure is actually very good in mechanical stability. If we do repetitive bending for 10,000 cycles, you see that the resistance of these biosensors remains the same. That means they are quite robust, especially toward daily usage in wearable platform. So this laser engraved microfluidics, as I mentioned earlier, is very important to minimize the influence from sweat contamination and the sweat evaporation from the skin. And we designed this multi-inlet microfluidic module that can sample sweat generated from the skin. So we can collect this sweat in the microfluidic. When new sweat come out, it will push away the old sweat. So we have this black dye to show, when new sweat come out, this black dye get pushed out. Showing, we can get a fresh sweat on the top of sensor. The sensor will be in the middle reservoir. So when we switch the target concentration from one concentration to another one, it takes roughly 2 to 3 minutes to reach the new stable reading. That means our sensor will have very small time delay. We can get close to real-time information using this microfluidic system. This is about using laser engraving to make larger scale biosensor at low cost. Not only using this approach, we could also using another interesting approach to make flexible biosensors at low cost. In this case, inkjet printing. Inkjet printer is our office printer. A lot of people are using inkjet printing as well. So we know that we need to use different type of ink. So how about we replace those ink with our nanomaterial ink? Of course, this printer is like a better version as well. We can use this printer. We can customize this ink. We can prepare, the ink consists of different nanomaterials. For example, we can consider ink made of silver nanoparticle, carbon nanoparticle, gold nanoparticle, carbon nanotube, graphene oxides, silver nanowire, MOF, or in some encapsulation polymer. All this material, we can prepare the ink. Then we can use inkjet printing to print a different type of material at different location to form different type of sensor, electronics. So the entire wearable system or electronic skin can be mass produced by using printing in this case. So this work was just published a few months ago in Science Robotics, with a feature on the cover. So this is another very interesting approach we can apply for mass produce this sensor at low cost. Another important question people may ask is, since you are doing sweat analysis, usually when you do vigorous exercise or on the high temperature to get a lot of sweat, right? So what if people, when people do exercise, people don't have sweat? If we want to use it in a clinical setting, we cannot ask our patients to wake up to do some exercise, right? This is not very practical for clinical use. We have to address one important question: how to access sweat without the need of exercise to make sure our device can be used by many, many people, right? Hopefully, could be potentially used by everyone, but we have to address this problem. By literature search, we found that there is a process called interferosis can be used to induce sweat locally. You don't have to induce sweat or the whole body sweating. We only want to locally induce sweat from a small area. Then we can sample this sweat using microfluidics, right? So basically, this interferosis is used in a clinical setting for standard sweat test. Sweat test is a gold standard to diagnose cystic fibrosis, which is a genetic lung disease. The doctors usually use this small equipment, apply a small current through the skin. On each electrode is 2 electrode pair, apply current. On each electrode, there is hydrogel loaded with drug. So the drug molecules can be delivered below the skin, such as pyrocarbon molecule. They can stimulate the sweat gland, trigger local sweating. So only this small area, the sweat gland will start to sweat. So the doctor will use this device to collect sweat, then send out this sweat sample to a lab to do chloride test, which is used for cystic fibrosis diagnosis. So inspired by this process, so we developed a miniaturized system that can perform localized autonomous sweat induction using interferosis through a very small current application. In this case, using laser engraved graphene electrode, we are using a very small graphene electrode pair by applying very small current, also only around 50 microampere. We can deliver the drug, such as carbacle in this case, below the skin. The carbacle will stimulate the sweat gland, trigger local sweating for a very long time. We only need to apply this small current for a few minutes. And the sweating process can last for 4 or 5 hours or even to 2 or 3 days. You can imagine that. You can easily repeat this process to realize long-lasting repetitive sweat induction, and we could potentially get a sweat continuously 24/7 in this case. I have this electrode pair. You see the shining part is hydrogel loaded with the drug. And drug, these are all FDA approved, and people use these on newborn infants. They are quite safe in general. So, and we are only using very small dose as well. I want to show you some video how sweat come out from the skin and sampled by the microfluidics. You see here, we put the black dye in the middle to let you see how sweat flows through this microfluidic. You see when sweat come out, this black dye get darker, lighter and lighter. Eventually, all the dye get pushed out in the outlet. This is another subject. Very quickly, you see the black dye get pushed out. So the sensor is actually inside the middle reservoir. We just want to let you see clearly how efficient sweat refreshing in the microfluidics. We can always get analyzing new sweat. So our lab not only developing these nanomaterial-based biosensors, we want to make sure we can collect reliable data, because data is the most important thing for this wearable sensor, right? All the healthcare application, personalized health, precision medicine is based on data. So we develop also the integrated system in addition to the sensor patch. We develop these wireless electronics, for example, that can perform interferences, perform multiplex, multimodal analysis, and we can also have this smart watch like a device as well with display. And we also have this cell phone app. You can real-time read the biomarker concentration and check their history, how the fluctuation of your biomarker level in your body during the physical activity, different type of activity, right? You can do exercise, you can do walking, even office work, even while you're sleeping, we can continuously sample sweat and perform this autonomous sweat analysis. So from these slides, I want to show you some applications. Firstly, we can apply this wearable sensor for disease diagnosis. Cystic fibrosis, I mentioned earlier, is a genetic lung disease. People with cystic fibrosis usually died at a pretty young age, and before the age of 40. So clinically, people use standard sweat test to do CF diagnosis. So you have to collect sweat using that small equipment and send out this sweat for a lab to wait 1 week to get data. So in collaboration with the Stanford School of Medicine, basically Cystic Fibrosis Center, we applied our wearables. You don't need to wait 1 week in this case. Within 20-25 minutes, we can induce sweat and analyzing the biomarker level in sweat, in this case, sodium chloride. So look at the patients and healthy subjects. Their sodium chloride level differ substantially. You see here, patient level, their concentration usually higher than 60, higher than 80, but for the healthy people, much lower, usually less than 40. So for adults, the standard for diagnosis is based on chloride higher than 60. So look at the data, and considering the gold standard, we can say that our device can be used for diagnosing CF. This is one application for disease diagnosis. And we can apply our wearable sensor to monitor different types of metabolic disorders. One example is gout. Gout is the most common inflammatory arthritis, affecting tens of millions of people around the world. My brother has gout as well. So gout is developed either because of genetic reason or lifestyle. So uric acid is a biomarker for gout. So if we could continuously monitor uric acid, because too high uric acid will crystallize near the joint for the gout patient, which trigger tremendous pain. For the patient, it's very painful for them. They cannot eat too much red meat, shellfish, or beer. If we could continuously monitor uric acid, it will be very helpful for the healthy people to maintain a healthy lifestyle, to minimize the risks for developing gout. It is also very helpful for the gout patients to look at the uric acid level routinely to avoid the gout attack. It is also helpful for the patients who is using medication to lower uric acid level, to real-time check uric acid level, to personalize their drug dose, not taking too much or too little medication, to make sure they take suitable amount of drug to maintain healthy uric acid level. By applying our laser engraved graphene sensor, we have tried on healthy people, male, female, And we also apply this on the gout patients in collaboration with Dr. Jiang Sai, Dr. Zhaoping Li at the UCLA Medical Center. Dr. Li is actually the chief of clinical nutrition at UCLA Medical Center. We can see that for the gout patients, their concentration of uric acid is very high, much higher compared to healthy people in both blood and sweat. And if we check sweat and serum biomarker level in the uric acid level continuously, we can see sweat and uric acid follow closely the serum one. And the correlation between sweat and serum is pretty high. We got a correlation factor of 0.864. That means we could use sweat as a source for non-invasive uric acid monitoring and gout management. We're running a larger scale clinical trial funded by NIH now on gout patients. So this is about uric acid monitoring, but many other metabolic disorders, pre-diabetes, metabolic syndrome, require us to monitor a number of other metabolites and nutrients. For example, a lot of amino acids and vitamins have close association to these metabolic disorders. And if we could know this concentration of nutrients, it would be very helpful to realize personalized methods through precision nutrition. If our body go to a wrong trend, can we do nutritional intervention? Just change what we eat, change it, through nutritional intervention, we can reverse the bad trend to maintain a healthy lifestyle, to minimize the risks to developing cancer, develop cardiovascular disease or type 2 diabetes. So, but these biomarkers, nutrients are very hard to detect previously because we don't have suitable enzymes or bioreceptors that can target these specific nutrients. It's hard to realize continuous monitoring as well. Many biomarkers like protein, we have antibodies to target, but these nutrients, you cannot find such antibodies. So in this way, we propose a new approach. We build artificial antibodies through polymer synthesis. We build a molecular imprinted polymer that can act as an artificial antibody to recognize the target. We can also generate a signal by incorporating a redox probe between the molecular imprinted polymer layer and our graphene electrode. So we can also regenerate this interaction to realize continuous monitoring. Based on this, we can demonstrate for the first time, we can continuously monitor every single type of essential amino acid and vitamins. So this allows us to track different type of essential amino acid. For example, branched chain amino acids. These are very important amino acids that are predictive of insulin resistance. So if we take some amino acid or vitamin supplement, we can continuously track this biomarker level or amino acid vitamin level in our body using this wearable sensor. Branched chain amino acid is predictive of insulin resistance. So we also identified there is good correlation between sweat and blood amino acid level. If we look at obesity subjects and obesity with type 2 diabetes, their BCAA level, branched chain amino acid, in this case, one type of amino acid here is leucine. Leucine concentration is very high compared to healthy people in obesity subject and the type 2 diabetes subjects. So we could continue to track this leucine concentration and give the user suggestion how should I maintain the lifestyle and the dietary intake to minimize the chance for developing pre-diabetes or diabetes eventually. So this is, you can imagine, very useful for us to really stay healthy. So one of the important applications I want to say also is stress monitoring. Stress is a very important health condition. It is related to 95% of diseases. Even it is so important, stress is very hard to measure. Right now, people use, standard is a questionnaire. You ask a bunch of questions, you get a score, which is very subjective, right? So depression is a similar way. We are thinking about if we can develop a sensor that can quantify stress and tell us stress level by analyzing biomarkers in sweat. In this case, stress hormone, cortisol is a very important biomarker, tell us stress level. So using this laser engraved graphene electrode, we can monitor cortisol level non-invasively by analyzing sweat. Why we don't use blood cortisol? Because when you draw blood, when finger prick or blood draw, you give your subject a lot of stress. You want to monitor stress by giving stress, that's by itself problematic. So non-invasive cortisol monitoring is critical. So we developed this sensor that can accurately and rapidly analyze cortisol level within 1.5 minutes, basically. We also tried to look at the cortisol level in sweat. We found that they have a very similar pattern to blood. And if we give our subject stress, we can rapidly see the cortisol level in sweat increases. We can use this as biomarker to look at the stress fluctuation daily. So, we did different stressors on subject. Each one we can see effective cortisol response. This is a very promising way where we are integrating physical sensor, chemical sensor, and we could quantify stress right now. By using a similar approach, we're not analyzing sweat, by using laser engraved graphene biosensor, we could also perform COVID-19 diagnostics. In this case, we developed this larger scale, mass producible, low-cost telemedicine platform that can simultaneously monitor virus antigen, virus antibody, and inflammatory biomarker within 10 minutes in both saliva and blood. And why we do multiplex sensing? Actually, the information collected in such short period of time will tell us 3 aspects of information. So whether we are currently infected by COVID-19, how is our immunity information? Now we have a vaccine, we still can monitor our immunity information, and how severe the infection is from this inflammatory biomarker information. So we can quantify this biomarker level very short period of time. We also tested the selectivity over SARS, MERS, these other coronavirus. We can successfully distinguish all the COVID positive samples and negative samples we tried. This is, again, a very promising platform, mass producible, low cost, and still perform multiplex analysis for COVID-19 diagnosis. The last piece of my talk, I want to briefly mention how we can power future wearables. We talk about many applications. More application means more power consumption as well. Right now, we are using a small battery in multiple cases. We're thinking of in the future wearables, not all the time there is electricity rechargeable. There is electricity available for you to recharge a battery if you run out of electricity. So since we are doing sweat analysis, we are thinking, can we use the sweat to power our wearable sensor? So in this case, we integrated a biofuel cell into our system. We built a biofuel cell powered electronic skin, biofuel powered electronic skin. We can harvest energy from human sweat by converting sweat chemicals, in this case lactate, into electricity. We built this battery-free system that can perform multiplex sensing, signal processing, and Bluetooth wireless communication using the energy fully harvested from sweat without using any battery. So we can reach very high power by integrating this 0-dimensional to 3-dimensional nanomaterials. We can get 3.6 milliwatt per centimeter square from sweat continuously. And we also integrated different interesting material, in this case, platinum cobalt decorated CNT as a cathode electrode that give us very good long-term stability. We actually have high power output and good long-term stability. In this case, we build this robust, fully encapsulated system that can reliably harvest energy from sweat and perform this multiplex wireless biosensing. So during the exercise, during physical activities, we can monitor urea, ammonia, glucose, pH, for example, continuously without using any battery. So in collaboration with another Caltech professor, we are actually developing a miniaturized electronic IC chip that can perform the energy harvesting, management, and wireless communication. The entire packaged system is very small. The chip is only 1.06 by 1.3 millimeter. Fully packaged system is 5.5 by 6.2. So we can integrate many other biosensors and signal processing circuitry onto the chip or into this small packaged system. We are having a new chip soon, which can process 25 sensor channels simultaneously and very small. The last example is briefly, we could not only harvest energy from biofuel cell by getting chemical, in sweat, convert sweat chemical into electricity. We could also convert mechanical body motion, mechanical energy, in this case, body motion into electricity by using a flexible printed circuit board based freestanding triple electrical nanogenerator. So we propose this platform that can continuously harvest energy from the body motion that can charge a small capacitor. Eventually, we can also build this fully integrated system that can simultaneously perform multiplex sensing, signal processing, and wireless communication without using battery, just entirely through energy harvesting from human body motion. So To summarize today's talk, I proposed this wearable biosensing platform that allow us to real-time multiplex analyzing a number of different biomarkers from the skin by analyzing sweat. So this really allow us to collect a large set of data from our daily activity. We could use this data for fitness monitoring, for disease diagnosis, and very importantly, this big data is not previously accessible. This will enable numerous fundamental and clinical investigation if we apply modern data analytic tools right now. In the end, I would like to thank my group at Caltech. We have around like 30 research members in my group. Thanks to their hard work, we have made this progress over the past few years. And also thanks to our collaborators for technology development and for clinical evaluation. And of course, our funding support as well. Finally, also happy birthday, HUST, and also 祝母校70岁生日快乐. And thanks very much for your attention. I'm happy to take any question you might have. Thank you.
Hi, Wei, very nice talk. Nice to see you again. Yeah, so it's so exciting to see, you have a new result, and especially during these 2 years, got some results for the, COVID. That's very exciting. So we will have a question and a panel discussions. So let me introduce all our panelists first, okay? Yeah. Sorry. Yeah. Today we have a big panel. Like I said at the very beginning, we have the host alumni from all over the world. So first the panelist is Professor Zhu Ying. He's now a lecturer at the University of Technology, Sydney, and he graduated from material science, right, in Hust in 2009. So as they short time period in Suzhou, and then moved to Australia, got her PhD there, and now is set up his new group, independent PI. So welcome, Professor Zhu. And our next, panelist, sorry, yeah, push wrong button. Yeah, as Xueming, Dr. Xueming Ji. Xueming was graduated from HUST and electrical engineering, but he was enrolled in HUST, was in the biomedical school, and then he changed his major and got a bachelor degree and engineer double E, and then moved to Germany, got his PhD in U2. And stay a few years at BMW. Everyone knows that as the best car, industry, and he be one of the managers there. And then back to China. Now is started up his own company. It's very, very nice company, growing very fast. 亮道 Intelligent Automotive. So he will introduce this later. So welcome, Xueming. And we got our challenger today is Ouyang Zhufeng as one of the youngest one as a challenger. He got bachelor degree and University of Science and Technology, Huazhong University. As a bachelor degree was in the material science, right? No, sorry, engineering, right? Engineering, energy engineering, school. So I moved to University of Tokyo, purchased his PhD, and now he's a postdoc at the University of Tokyo. So yeah, we have a very large group here, and now welcome everyone to get on the stage. And as usual, we start our question from Ouyang Zhufeng. Yeah, challenger, please.
Okay, so here I have one question for Professor Pong. Thank you very much for your very enlightening and very inspiring report, which is about the large capacity and high charging speed sulfur batteries. So I have a question like how is the degradation rate and what is the estimated lifespan of this sulfur rechargeable battery? Yeah.
Chen, you mute, please.
Sorry. Yeah. Thank you, Zhufeng. Yeah, there are many types of sulfur batteries, and one of the key the key challenge is the cycling life. For example, the lithium sulfur batteries has been studied for like at least 2 decades, and there have been numerous papers on this. So the degradation rate or the cycling's life, if we speak about lithium sulfur batteries, that can work for like thousands of cycles in the lab. But if you make a practical battery that can like make, for example, 500 watt-hour per kilogram, it's a very high number. The cycling life will be less. For example, like 200 or even less cycles. So that depends on the like how you make the cell. But for the aluminum sulfur batteries, currently we have demonstrated about like for at this moment we're able to cycle the cell for like 2,000 cycles, and that's not very that's not to the the satisfactory yet, but I think they're still it's still very promising. Yeah.
So the degradation rate also because of the sulfur, the chemistry reactions about sulfur is very complicated. So many other like some byproduct will appear during the charge or discharging process.
Yeah. I think the goal or my goal in the past few years on lithium sulfur batteries is to increase the second life. Yeah.
Okay, cool. So we can move to Zhu Ying.
Thank you very much. So I have some questions for Professor Wei Gao. That's very nice talk. I think one of the best talk that I have been ever listened to in biosensor field. And I guess your group member must work out a lot during their research project, which is good, doing PhD study. Okay, so I have one question related to, like you mentioned about the biosensors using in precision nutrition, and how are you going to like specifically detect different type of amino acids? That's one question I think I missed out in your talk.
Mm-hmm. Yeah. That's a good question. I didn't get time to expand in detail. So I mentioned earlier, so we don't have a suitable receptor naturally, like antibody, enzyme, for most of these amino acids. That's why we build this artificial antibody, but essentially molecularly imprinted polymer. So we actually polymerize the monomer along with the target amino acid. Then we form this polymer layer, which traps this amino acid inside by extracting amino acid out. So amino acid, after amino acid removal, there is a certain cavity left in the polymer. That cavity has the same size and shape with this amino acid because the initial amino acid stays here. Then we can use this cavity to recognize the amino acid in the body fluid, which is essentially the same mechanism how antibody antigen recognize each other, shape recognition. So yeah, we by incorporating this platform onto our laser engraph the graphene and biosensor, we put in the middle layer, we put a redox probe, give us signal. When you have a target bonding to this cavity, that will block the access of this redox probe to the sweat. That will cause the redox probe signal change. We monitor this signal change to get the amino acid concentration.
Thank you very much. I have another question. So quick one. You didn't talk about commercialization, but I guess that some of your development has been commercialized. Can you share some of the information?
Yes, we have been considering. I don't have a company yet, but basically every week we get some investors contact or companies request for collaboration. So probably in the next year or two, you will see a startup company from our lab, and we do have strong interest to commercializing this technology. As you can see, we try to push effort to low cost mass production and build a prototype and evaluate this in a number of healthy and the patient populations basically. And there are some other companies, for example, from John Rur's group. He also started a company on sweat test, but it's a very different mechanism. They are mainly doing microfluidics and optical sensing, and we are mainly focusing on electrochemical detection. I hope not too long away, you will see the major progress in the commercialization effort. Yeah.
Thank you.
Thank you.
that's a very good tradition for the HUST students to start the companies. Xueming was one great example. Xueming, did you have questions for them?
Yeah, sure. First of all, very nice to be here, and thank you for your introduction, Alice. Since I'm from automotive, so I would like to raise a question to Professor Pang. And this battery market in automotive is booming, and we have the CATL with a value of 1,000 billion. So it's a very prospective. Could you please summarize, the pros and cons having the sulfur battery for the potential application in electrical vehicles? Because I mean, the consumer, they care a lot about the cost, about the safety issue. They are also very anxious about the range. So could you please first, list those pros and cons?
Yeah. So thank you for the question. If we talk about the batteries for the electrical vehicles, I mean the current market is basically two options. That is in China, in the China market, is the lithium iron phosphate battery and the nickel manganese cobalt, what we call is NCM chemistry. So those two chemistries are very mature technologies, and for example, the lithium iron phosphate has a bit of lower energy density, but it costs less, like the material wise costs less, and the NCM battery has higher energy density, but it costs a little bit more, and the safety that comes with the higher energy density is a problem. That's basically for any battery. If you go to higher energy density, you probably end up with a less safety, like chemistry-wise. So for the sulfur, the pros, the advantage is of course the advantage is the cost, and I think the cost is going to be like probably not in the next 5 years, but in a very long run. I think the cost of the materials is the main determinator on any battery, because the cathode part of lithium-ion batteries cost about half of the battery cost. So I think that's the pros, like the important thing about the sulfur chemistry. But the cons, one of the disadvantages that has already been mentioned by Zhu Feng is about the cycling stability or the cycling life. So we have to work even harder on how to improve the battery to cycle, for example, 1,000 cycles at a practically high energy density. So to that end, I think lithium sulfur or aluminum sulfur batteries will be able to enter the market if we are able to solve the problem, for example, with the cycling life, and also to make it a practically high energy density. And the other thing about the sulfur battery is about the all solid state battery, which is also one of the fields that is going on in our lab. Is that for battery to be able to use it in a car, like has to be, as I said, one is cost, second is high safety. Like you don't want to drive a car that is not safe, right? So all solid state batteries can make the battery very safe, and I think, for example, also lithium sulfur battery, one of the main projects in our group is very promising to offer both cost and also the safety. Yeah, I think that's part of my perspective.
That's great. Okay, Chen Rong, how about you? Rong, you're mute.
Yes. Actually, I think both are great talks. I really enjoy it, and it's definitely bring the academic fist. I actually have a question to Professor Gao. It's really generates my interest because you mentioned your commercialization of the sensors, And you showed us a few applications like the gout, diabetes, and stresses. So could you give us some comments or your perspective? Which one probably going to be the first or the killer applications for this kind of device? Because I think all of them sounds to be very important.
Well, it's hard to give one, but at least I would say I have two on the top of my list. One thing is about nutrition. We are running a lot of studies right now, working with the UCLA. I think nutrition is very important, naturally fit of wearables. Wearables are not intended for diagnostic, let's say. Ideally, if give people early warning to help people maintain a healthy lifestyle, to make people not developing diseases, that's the ultimate goal. So that's why we have a lot of effort developing this, monitor these nutrients, metabolites, and we are actually giving our subject different type of diet. Our collaborators, very interesting study. They ask their subject eat 1 month, avocado or strawberry or this to see how they're healthy. And we also have surprisingly a lot of collaborators, even on cancers, they're on the cardiovascular disease, but they do a lot of trials to look at diet influence because they think the diet could be one of the best cure for these diseases as well. This is one of the top on my list. Another way is always because there is stress. Stress is such a big topic, right? To look at stress hormone or to look at other stress biomarkers, how to quantify the stress objectively, I would say. Yeah, we have a major support from NASA, from Navy as well, to look at really using the multimodal biosensor to quantify stress. I think that's another also very promising direction. It's hard for me to pick only one, but I think these two are among my top list for now. Yeah.
Yeah, that's great because I saw a lot of stress sensors that tends to be invasive, non-invasive. So you put all the sensors on top of your head. It looks a little bit scared, especially for children.
That's right. A multimodal. People look at a physical parameter like heart rate, blood pressure. They're not very powerful by itself. So that's why we're looking at the chemical and physical together. Multimodal system give us more comprehensive picture about the stress response in our body. Yeah.
Great. Thank you very much.
Okay, so I follow these questions to Wei. So Wei, you say that maybe for the wearables it's not go to the level for diagnosis, right? So because the precision is still a limitation, but you want to go to another way. But did you consider to collaborate with herbal medicine people, like Chinese traditional Chinese medicine? They also give a lot of suggestions or advice to all these kind of diet, all these things. Did you collaborate with them?
Yeah, we haven't really talked. That would be a very interesting direction. Even think about Chinese medicine. It's a matrix. You eat this Chinese medication, there is a matrix of a different compound influence. Many substances actually we could monitor from the skin. I have a very important topic I didn't talk given the time limitation. We're looking at all these substances and drugs. To look at how these substances affect, or how we can know how much level drug is needed to control the dose. Because no matter Chinese medication or Western medication, how much dose is very important. If we have too high dose, it will have a strong side effect. So we have a major collaboration with here, a cancer center. We look at a number of cancer drugs. I think a Chinese medicine is a very interesting direction. But here I don't have good collaboration on that direction, but I'm open to that. That would be very interesting. Yeah.
You are found one. You're good. You're good at the collaboration. You have so many great collaborators. Yeah. So I have another question for Quanquan. Yeah, Professor Pang. So actually, to talk about the energy, talk about the batteries, always the efficiency is one big issue. So could you please give some perspective for your technology, the most challenging part, how to enhance or promote, improve the high efficiency?
Yeah, thank you, Alice. So the energy efficiency it is very essential here in energy storage because it determines how much energy you can give out by taking in like the energy. So, but lithium-ion battery, so the benchmark energy efficiency of the batteries is rather high. For example, it can be 80% or even higher. It's much higher than like other technologies. If you name a few, but the our technology, for example, the aluminum sulfur battery that works at 100 degrees C, it has even higher energy efficiency. That can be like 92%, and that's because the kinetics of the reaction is very fast, meaning that you will like spend more energy. You will like consume less energy in the impedance or in the ohm impedance and stuff. So I think it's not a big problem in our technology, but if you talk about efficiency here. Yeah.
Okay, that's great. I think that's why you work with, got so many attention, right? Draw so many attention. That's one of the best part. Okay, yeah. So we're so proud of all these young, alumni here, right? Yeah. So now, Chen Rong, I think we can move to the second part.
Sure.
Okay, we switch. So sorry, go back. Yeah, we switch. Sorry, we switch for the language. Okay. Yeah，因为今天是一个非常快乐的校庆的环节啊，所以我们想着我们校庆的时候下一半段还是用汉语，可能大家要表达的比较充分一点，因为我想每个人可能都在学校有着很多的故事啊。前面我们在放这个视频，放大家祝福的时候，也有很多的这个很感人的这样的一些细节啊，包括陈刚老师，其实昨天我觉得他的分享特别动情，因为他在华科的这些年讲出来给大家这个感情是非常好。那今天又是我们校庆的一个特别的 part， 我想是请到这么多来自世界各地的这个校友啊，非常的不容易。所以呢，我们也希望借这个环节让大家分享一下。陈荣，你看咱们怎么分享比较好？
可以呀。首先我想可能给大家提个问题吧，因为其实我自己并不是华科的，我没有在华科读书，我是可能在你们所有人中唯一一个没有在华科读书，但是在华科教书的人吧。所以我特别想听你们分享一下你们在华科做学生的时候的一些感想，因为尤其是师生之间的这种关系吧，特别是像高伟昨天这个。我们在那个大会上，陈刚老师的分享，他提到了一个 alumni 的 visit， 然后 surprisingly you are here today 。
高伟，你先。
对，上周是因为我在MIT 做一个 seminar， 正好有机会，很荣幸也是见到陈刚老师。我觉得我在华科的4年，给我最大的感想就是。我觉得我们的学风比较扎实，就是大家都是在脚踏实地的做科研做工作，去解决一些实际的问题。这也是我觉得得到一个最有意义的一个 training 嘛。我们就是 identify 就是提出具体的问题，去解决具体实际的问题，通过我们自己的踏踏实实的工作努力去解决一些。重大的国家社会需求，而且就是这个学风来说，直接影响了我们就是整个学术生涯，我觉得对我们就是怎么说呢，非常大的收获，也是直接就是让我整个的学术之路就变得相对顺畅一些。我觉得在华科的4年，培训是非常非常关键的。就是。
哦，那你这么说，是不是华科老师都很严厉呀？
那倒没有，
要学的这么扎实，是不是都很凶啊？
我觉得你是会从一些课堂啊，能感受到老师严谨的态度，但是其实我们跟老师的关系其实都是很融洽的，我们学生之间的关系也非常融洽。总体来说，因为我在就是本科的时候并没有参与到太多的就是在实验室的科研中，但是我有一个非常深刻的印象，就是学校有很多创新活动，然后我们可以一起参加，有很多跟老师的交流，去比如说就是设计一些 小型的机器人呀，还有一些当然从小型的机器人比赛到大的就国家 level 的比赛，都会有很多的就是学生之间的合作，给老师之间的交流，这个对大家的动手能力也是个非常大的锻炼。总体来说，我觉得。
这个我必须得插话啊，因为这个搞学生比赛、搞创新，这个我可真的擅长。对，而且这个华科的同学确实是因为华科启明学院刚刚成立的时候啊，第一场讲座可能就是我去做的，因为当时我刚刚开始这个 ICANN 的比赛也在全国推广。我印象特别深刻的是，这个比赛后来在华科这个比赛的成绩是非常好，出来的同学也让我印象特别深刻。就比如说有一个同学，其实他当初刚刚进大学，他要参加比赛的时候，他就启明学院是非常好啊，在全国也是特别好的一个，他把华科这些非常优秀有想法的同学就集中起来，可以去做些创新，组成小团队。那这个同学呢，他当时就想啊，进学校以后让他找东西，很多人送东西不好送，他就做了一个彩虹式的这样的一个可以放外卖的，直接找到的这个箱子非常好。我想讲这个是干嘛呢？后来有一次特别巧，我到这个国防科大去，他在那儿读博士了。他过来跟我讲，老师你记不记得我啊？当时我做第一个项目的时候，我就觉得我对科研太感兴趣了，太好玩了。所以后来他就继续在这条路上做得非常好。现在那个孩子从华科毕业，在国防科大毕业，好像后来又出国交流，但是非常优秀。所以我觉得这个确实是华科训练学生的一个特别好的一点，很多学生在这个过程中训练的就是特别的 solid。我觉得我这个刚才其实这个高伟想说也是特别的 solid， 就是你的技术很扎实，你的知识很扎实，然后能够去做事。这个是我从外边看啊，对我看到华科这个训练非常好，所以感谢陈荣这样的老师啊，对我们大家都照顾的非常好，带的很好。对，其他的同学我们再点个学明，你这个后来创业是不是跟在学校训练有点关系啊？
我觉得还是肯定受益的，因为首先我觉得我代表的不是说在华科就是最怎么说呢那种学霸的那个类型，我是相当于在这种学在华工的这个氛围里边属于玩的比较多的，也是怎么说呢，在这个学习的竞争中提前经历了各种各样的这种打击，被学霸去打击，这个对我创业实际上把自己的心态呀提早的磨练，我觉得这个是有很大的帮助。另外，刚才张老师提到的这个师生关系，我们原来电子系实际上有一个甚至在华科很有名的叫张妈妈张丽娜老师，实际上她从入学她不是专业课的老师，但是对于我们整个这个本科期间的这种从学习到生活照顾的实际上非常的无微不至。然后到现在上也跟我们从电子系毕业的很多的这个学生还提供，比如说现在帮助我们去联系，因为我们现在很多半导体跟这个芯片相关的嘛，介绍之间的不同届之间的一些学姐学长啊学弟啊，互相的去在我们这个创业领域或者工作领域帮我们去做一些拉齐，这个我觉得里边受益非常大。
哇，这个太感人了，这个有点，这个真的太感人了。毕业这么多年了，学明你好像00几年就毕业了吧？现在还跟这个张妈妈有联络，对，她还在帮助你。
我们现在实在是就有的时候刚找一些资源啊，包括在这个，比方说找一些 foundry 啊，找一些芯片的一些专家，实在没有办法的话，去找张妈妈，张妈妈一定会把一个关键的人给你推过来。
陈荣回去找一下这张妈妈啊，在学校需要更多这样张妈妈、李妈妈、王妈妈全都需要啊，这个对学生帮助太大了。
是的，我觉得这个也说明了，我觉得作为一个学校吧，最重要的就是给校友们建立一个 network。我刚才也说了，我们70年培养了这个70万的这个学生，所以说那是一个相当大的一个 network。所以说呢，我也后面我觉得大家也可以分享一下，就是你们在特别是很多这个科研工作需要有 network。做创业那就更需要有 network 了，可不可以从这个方面呢分享一下你们的比如说合作啊、友谊啊，还有各方面的 network？ 要不全先说一下。
行，我谢谢陈老师。我可以从另外角度分享，就是 我之前这怎么讲，就是在华科的时候，这个会议最多或者说交的朋友圈最多的是，其实是在运动过程当中。我之前其实打篮球，所以说不管是印象最深的当然是新生杯的时候，当时刚入学啥也不知道，当时从山东来到武汉，觉得来到一个奇异的这个让我很开眼界的地方。但是我谁也不认识，但是新生杯让我就融入了这样一个环境当中，然后直到后来，包括各种比赛，其实包括在运院或者在我们打球的时候，其实交了非常多的朋友，然后包括我的很多学长啊等等，包括其他学院的，所以说这个华科的运动氛围，包括足球和篮球，我觉得都是在我后来包括出国去加拿大或者去美国，甚至回到北京来，都是让我就让我觉得是氛围非常非常之好的一个地方。我不好说比其他学校这个好多少，我敢保证肯定是非常好的，所以说这也给我们很多的这个 connection network 也可以是 network， 然后当然也是很多都是可能是一个一辈子的好朋友等等。所以
我怎么找到你的呢？圈圈，就是因为你跟韩凤迪一起打篮球。
对，
对，他们这个很有意思，因为韩凤迪也是华科的，现在也在北大生物医学工程系，是个青年教师，所以呢，他就打篮球，
一起打球，
对，一起。其实大家在学校的时候可能都有非常多的这种运动的经历啊。提前我跟这个欧阳朱峰同学聊的时候，他还说哇，运动。对，朱峰，你有什么故事分享？有没有登珠峰啊？
到那个是今后的目标，现在还没有去过。那个运动的话，其实我也觉得，像虽然说是学在华科，但是其实华科的生活是比较 balanced 的，就是一方面学得很扎实，但是晚上一般下了晚自习，我看就在我当时在华科，我在华科待了6年，基本上晚上不管是中操也好，还是西操也好，还是东操也好，晚上去跑步散步的人大家都挺多，大家都非常享受这种就是晚上去东9去自习之后，然后去操场上挥洒汗水，然后再回去休息，大家都很享受这样一个过程。然后期间我也是很喜欢参加那个华科的那些夜跑，就夜跑玉家山啊之类的，然后也是认识了非常多的朋友。我还记得其中有认识一个学长，现在我跟他还有联络，他在迪拜的那个阿卜杜拉国王大学做博后研究，然后我和他现在还有联系，是因为我在博士期间当时遇到了一个我遇到了一个那个研究上的问题，然后我想起来他是做燃烧方面的，然后我就去问他，然后后面我们联合一起解决了一个小问题，然后发了一个小 paper， 然后觉得也是不可多得的一次那个 connection 吧。
这个故事太感人了，我觉得那个。不过有一个好消息啊，就是咱们的那个玉家山上现在修了那个新的绿道，这个绿道非常适合跑步和骑车，而且它能够连到我们的东湖绿道上去了。所以说加起来是100多公里的这个绿道，如果你能跑，你可以跑几个马拉松。
对，超级马拉松都直接有这个选择了啊！
是的，
太厉害了，100公里
的出发
，100公里。
这个说这个 network 说这个运动啊，就是特别多的故事，这就打不住，因为我就是排球，他腿都打断了，在华科的时候，就是这个非常的有意思。华科确实运动是很有这个其实这里边这个 network 里面，我觉得 network 最紧密的是朱颖对吧？朱英。为什么？因为朱英的先生也是华科的。对，朱英，你分享一下你的这个 network。
好的，就是既然张老师 Q 我了，我就稍微分享一下。我和我先生都是材料学院05级一个班的，然后我们是同班同学，然后也是就是说一直以来就是说华科毕业之后一起去了苏州。然后后来又来到澳大利亚读博士，然后读完博士呢，又去美国待了一段时间，然后现在又回到澳大利亚，所以就是一路以来就是说互相扶持吧，然后一直到现在就是2个人带2个孩子在家里面，也是对战友吧。
这说明华科这个气氛非常好啊！ 不只是有这个球场上的这个球友战友，也有家庭中的战友啊。对，这个也非常非常好的这个故事，在材料学院当时女同学不多吧？
不多，但是呢，就是除了我们班，就是我和我先生之外，还有另外一个班，也有一对儿，也是一直走到现在，然后现在是在加拿大。对，
所以对我们华科要有美好的印象，就是过来了以后，不光是有学霸，对吧？还有这个非常好的这个机会啊，认识这个终生的这个伴侣，这个特别特别开心。就是大家一分享这个就非常多啊。其实我想分享一个，陈荣，我可以分享一个吧？我觉得
当然，
我觉得这个特别好，就是校友的这种感情，它是很特别的。因为你不管什么时候你遇到，就会觉得特别亲切，哪怕你不是以前在学校里一起打球的啊，不是一起干什么，但是你在外边遇到了也会特别的亲切。所以我就想说，其实高伟呢，我们之前有一个特别有意思的故事，就是我们有一张很好的照片，我高伟还有王力宏一起在 Caltech 照的那张照片。其实跟我们照那张照片呢，也是一个华科人。是宋宇，对，所以呢，正好是4个华科人。我说这个呢，其实它是一个很好的这样的一个，不仅是 network， 而是更多的时候其实心里有亲情，大家在一起遇到了以后会感觉到特别的亲切。那么大家有些合作呢，这个机遇也非常的就是顺畅。因为这个高伟之前我也不认识，尽管其实应该是就是同时认识的人比较多。你比如说他的导师邮政。现在是校长，也是我的师兄，对，但是之前也没有这样联系，但是在华科开会的时候，一下遇到高伟，哎，就会觉得啊，真的是很亲切。然后之后有这样的一些合作，包括我的学生，其实宋宇是华科的，然后后来在这个高伟这边做博士后做 postdoc 也很顺畅。就我觉得这个校友之间他会有这种。这是一种像亲人一样的一些感觉，一些这种连接，然后大家合作起来呢也会比较 smooth 一点，这是可能是其他没法替代的。所以有时候我经常在讲，我说可能这是一个学校这种母校之间的感情，校友之间的感情，它有点像你的人生事业上的一个 family， 然后你相互之间会有这样的一些就是亲情之间的这种链接，大家在一起遇到会非常开心。像陈刚老师，我那天昨天在准备我就找到2012年的时候我去访问他，然后其实我带的是北大的学生，但是真的我带了北大一个班的学生，因为做创新的交流活动去陈刚老师 MIT 去访问，但是陈刚真是把全家都动用了来接待我们，不只是因为他学校关系他全家都动用都来接待我们。就是我是觉得这种 support。这种互相这个 connection 是非常就是打动你心的那样的一个感觉，所以现在大家在一起有一些这样的这个校友交流的机会是特别特别嗨的。我反正是觉得感觉比较嗨，因为1年前陈荣跟我说组织这个活动，我当时就激动了，我说必须组织对吧？因为这样可以把大家连接在一起，这是我自己一个非常 personal 的这样感情我也不知道大家是不是也有这种，就是觉得你在合作中，在其他中有同学同事之间是校友会更亲切一些。
是的，我觉得其实怎么来说，咱们学校这么大，然后各个学科也都很全，然后大家可以其实是有很多很多的机会，通过运动通过各种活动来建立起很好的这个 connection。今天有一个也特别值得提的，就是我们在这个咱们这个活动，就是咱们 IPX 今天正式之前，我们其实播放了几段视频，有我们这个母校就是学校相当于这个活动正式的视频，同时呢也有一个我们在 B 站上找到的一个咱们的本科生这个 UP 主他拍的一个就是学校的校庆云游这个视频，所以我觉得非常的多才多艺。本来呢，我们昨天晚上有一场特别盛大的这个在中超的这个叫什么文艺演出吧，那个文艺演出还有什么灌篮高手很多就是追忆大家青春的一些曲目。不过由于这个下雨的原因呢，就还没有正式的就是launch。我想就是最后他肯定会 launch 以后，大家也可以在视频上去看到，就是去追忆一下自己在华科这个非常有意义的这些岁月吧。
对，其实华科同学确实是很多才多艺啊。昨天看那个视频在网上找的时候，我发现真的特别感人。他配的乐也很好，他整个那个画面也很好，他那个网名也很有趣，叫亚油机。我看到这个网名叫亚油机的时候，我在想这个学生会不会是什么？就是刚才跟这个我们这个欧阳珠峰同学一个学院的呀，能源学院的呀，结果后来发现他还是电子系的，是不是？对，就很有意思。其实，在学校的时候，可能你身边有很多这种非常有意思的同学，那将来在这个这个人生这个道路上，可能会有很多有意思的这种故事啊。每次回想起这些时刻，可能也觉得特别好。那我能不能最后再占用一个机会啊？对，我其实特别想讲一个，就是让我特别感动的事情。其实我觉得华科对我影响最大的是我的导师，对，就是我们的杨舒子老师。就我真是觉得我人生的改变是因为他。对，我觉得杨老师，大家都知道啊，就反正华科觉得这是永远的校长，就是他是我的导师。但是他不一样的就是，说我在学校的时候是一个特别调皮的学生，可能就是属于那种永远都不听话、永远都在惹事的那种学生。但我发现，就是老师对你的改变是什么？就是因为他真心的想帮你，他真心的爱你，所以他就不会就是因为你调皮，因为你不听话，因为你老惹事而放弃你。对，所以我是觉得整个在这样的一个求学的过程中，会能够特别的感觉到，就是以杨老师为代表的这些老师啊，他真的特别帮助我。为什么我说杨老师为代表呢？因为杨老师的这个太太，这是我的师母，是徐慧碧老师，是这个生命科学学院的院长，他正好是从北大去的华科，对，去的华科，对，所以我师母对我也是特别的好，就非常的来关照你。非常的来帮着你做这些事，所以我觉得在华科有这么一批老师啊，是真正的这个核心，就是他会真正的爱学生，就是带你不光是上课，就高伟说上课对你要求很严，对吧？学得很好，带你去做竞赛，然后也会很尽心，像张妈妈这样的，就是一直对你很关心。其实华科是有一大批这样的老师，那我不能说100%啊。但我觉得华科这种老师是非常多的，所以我们在这个就是年少不更事的这个过程中，有幸到这个学校里来，可能真正的人生很大的进步就在这个过程中发生了，因为你遇到了这么好的老师，他带着你在前进，你遇到这么好的老师，他在指点你，所以我觉得每一次，其实我想起这个情节的时候，我就觉得，哎呀，这个真的就对母校那个感情，就像对家的感情是一样的，对你永远这个心都在那里，永远都跟他在一起。所以我觉得，真的非常感谢这个华科的老师啊，当然陈荣你现在是代表啊，我们大家谢谢你。对。
是的，非常感谢就是大家的这个分享。我想呢，咱们时间也差不多了，就看大家能不能用一句话对我们的母校献一句祝福吧。然后，好吧，Alice 张老师，
好的，可以。那我压轴还是我先开始？
你压轴吧。
好的。
咱们就按今天这个出场顺序，从庞全全开始吧。
行，是那我2句话吧，陈老师。
可以。
首先是非常遗憾，没有能够因为疫情原因没有能够现场去，去华科去母校，也没有能够去学院去参加这次校庆，非常遗憾。但是我想要通过这次机会，也感谢通过张老师提供这个机会呢，我也祝我们母校70周岁生日快乐希望在未来的30年。能够在100多岁的时候，能够再次回到母校，为母校过生日。好，
谢谢。然后我们请我们的高伟老师。
在这里我就祝母校70岁生日快乐，希望母校蒸蒸日上，蓬勃发展，再创辉煌吧。
谢谢。好，那我们下面一位是我们的 X Challenger， 他今天的欧阳同学。
好，那就是在这里我也祝华科70周岁生日快乐，然后我也希望 我和华科都能够同时的努力，就像是今天我以母校为荣，我希望今后母校能够以我为骄傲。
谢谢谢谢，好的，然后我们朱老师。
我也是，祝母校70岁，生日快乐，再创辉煌。然后我真的非常希望，就是说，在接下来的一段时间能够有机会，就是说回母校，带着孩子回母校去看看。对，
非常欢迎，非常欢迎。好，请我们的学名。
我的德语是在华科学的，用德语来祝福母校吧。Herzlichen Glückwunsch zum Geburtstag。也希望更多的这个华工的学弟学妹加入亮道，我们一起做让华工骄傲的公司。
好的，好的，非常感谢。好的张老师。
OK，
好了，
压轴Hast my heart, all the best。OK，
非常感谢大家。
好，那我们今天的节目就这样，就非常非常的开心啊！谢谢大家。今天我觉得是一个很特别的这个日子。当然了，节目还没有结束啊，全，这是你的 certification。OK， I can ask give everyone speakers for this certification. Thank you for your wonderful talk. Connect world and universe. 谢谢。
好，谢谢 Alice。
OK， Hi， 高伟。So this should be the second time you got this certification, right? Last time the color was blue, this time the color was red. So you get on another stage. So it's really seldom people, to get twice chance on ICANX. Proud of you.
非常感谢。
Okay, thank you. And next week we're going to have a light rising stars. So stay with us on ICANX. Celebration of past 70 years anniversary. This session is over, and we're going to looking forward next 70 years. Okay, thank you. I see you next week. Bye.